Okay, just to talk briefly about Newton's laws, you can read through my notes there of the three laws. I just wanted to highlight a few things. First of all, the first law basically is also called the law of inertia. It essentially says that objects will keep moving or stay at rest unless a force, an unbalanced force, acts on it. Instead of using the word unbalanced force, we're going to use the word net force. So in other words, just because an object is moving doesn't necessarily mean that there are overall forces acting on it. It'll move based on its own accord. Again, don't fall into the trap of Aristotle type thinking, where you actually need a force to keep an object moving. You'll keep relapsing into that. It's easy to do, but understand here that no forces are needed to keep an object moving. Forces are needed to stop an object or change its direction, and to keep it and to accelerate it essentially. The second law there essentially says net force is equal to ma. I like this better written as net force divided by m. The reason this is better is because it says that an object will accelerate more if I push with an overall harder force, or an object will accelerate more if it's lighter. In other words, if it has less mass. This is a very useful equation. We'll use this over and over and over again. But anytime an object accelerates, it'll have a net force, and vice versa. And also, the net force and the acceleration will always be in the same direction. Okay. It's pretty easy to use this one. Essentially, if I go, this is number 2, second law. It basically just says that if I take an object here, and an object that's 1 kilogram object here, and I push with 10 newtons this way, and someone else pushes with 20 newtons this way, and someone else pushes back with 5 newtons this way. Well, the net force on this object would be 10 plus 20 minus 5. I'm going to make this direction negative. So 10 plus 20, 30 minus 5. So the net force on this would equal 25 newtons. The mass on this object is 1 kilogram. So in fact, this object would have an acceleration of 25 meters per second squared in that direction. Okay, there's the second law. The third law is very, very tricky. Okay, the third law is very, very tricky. A lot of people use the word action-reaction. I'm going to say stay away from action-reaction. Basically, with every force, there's an equal and opposite force. That's what Newton essentially meant. People can understand this in a variety of ways. They usually say, well, okay, if there's a wall here and I come along and I'll draw my nice picture here. I come along here and I kick that wall. If I kick that wall, well, I feel the force on my foot as well. And so whatever force I put on the wall, that force is equal and opposite back. That's easy for people to understand. What's difficult for people to understand are things like Newton's second or Newton's third law in terms of other forces, like, for instance, non-contact forces. Okay, a non-contact force would be something like the Earth, okay, in force of gravity. If I have an object, and I'm just going to have an object here suspended above the Earth right here, it's floating above the Earth. Well, if I drop this object, there obviously are forces acting on it. Okay, it will accelerate. It'll actually accelerate at around 10 meters per second squared. What is causing this acceleration? Well, the force of gravity to this Earth. Okay. Well, Newton's third law, it's kind of difficult to see. Obviously, I'm going to call this the object and this the Earth, and I'm going to say that on this object there's a force of the Earth on the object. I'm going to call it F of EO. What this means is basically the force of the Earth on the object, okay, which actually ends up being the force of gravity. That's what we normally call it. I'm going to call it EO here. That's the force. Where's the equal and opposite force here? It's kind of difficult to see. Well, it turns out that if the Earth pulls on the object must be pulling up on the Earth. The object must be pulling up on the Earth. And in fact, these two forces here, FEO, has to be equal to FOE. Okay, a lot of people don't see that. Well, wait a minute. This object we can see accelerates at around 10 meters per second squared. Why don't we notice the Earth accelerating? Well, there's a big reason for that. This has a force acting on it. This has the same force acting on it. But recall that the equation is net force divided by mass. Okay, divided by the mass. Well, if they each have the same force acting on it, and that's the only force, that would be the net force on this object or the net force on the Earth. But this object has an incredibly small mass, and so it accelerates at this. If we use that same force on a massive Earth, okay, we won't notice its acceleration. But believe me, it does actually accelerate, but it's so insignificant that we can't perceive it. But it does in fact accelerate. It has to, by Newton's third law.